So in the textbook, you've been learning about OLS, or ordinary least squares regression. And what you're told is that least squares can give you an accurate estimate of the population parameter given a set of assumptions from a set of sample data. So how do we know this is correct? Well, one way is we can mathematically prove this. So here I have some notes that I took from my courses in statistics a long time ago, where I have a proof that OLS is unbiased. And by unbiased, we simply mean that the sample data estimate from OLS will converge on the true population parameter in an unbiased way. And this is simply the formula that shows that's mathematically true given a set of assumptions. A second way, one that I think is probably more convincing for you, is to actually show you that this is true. Now, how can we do this? Typically, we have populations where the parameters are unknown to us, and we're using sample data to estimate these population parameters. So how do we know we're getting the correct answer? Well, another way is through what we call Monte Carlo experiments or simulations. And what we do here is we end up generating population data where we know what the population parameters are, and we know what they are because we're generating the data and we're generating those parameters. Then what we could do is run OLS on samples of that data again and again and again and see if we actually get the right answer. And that's what we're going to do here. So what I'm going to do first is create X, which is going to be a sort of an independent variable. And so I use our norm function and tell them I want 1,000 observations of X from a normal distribution with mean 0 and a standard deviation of 1. I type in X, and you can see I get a whole bunch of different values there. The mean of these values is pretty much 0. The standard deviation of these values is pretty close to 1. Not exact, but pretty close. I'm going to do the same thing and generate some error. This is just going to be random error that's generated through a normal distribution with a mean 0 and a standard deviation of 1. And then what I'm going to do is set the population parameters. The first population parameter is going to be the constant, or the intercept, which is going to be 5. So I type in constant, and you see I get 5. And then I'm going to have the beta coefficient, or the population parameter that we really want to estimate, and that's going to be 10. So you type in beta, that's 10, right? And I'm just choosing 5 and 10 at random. You can put any number that you want here. Then what we're going to do is generate Y, or what would normally be the outcome that we're interested in explaining in a theoretical model. And so we're going to say Y is simply a linear function of a constant plus beta times X plus epsilon. Okay, and so then we get a whole bunch of different observations of Y. So what do these things actually mean? Well, imagine Y is some outcome that you want to explain, and that could be, say, Obama's popularity, or the popularity of any political candidate, or it could be how liberal conservative political candidate is. It's an outcome that varies on a continuous scale, and you might say that outcome is a function of some constant value, right? So maybe if this is Obama's popularity, then the constant value of his popularity might be some mean value in the population, some equilibrium value, and let's just say 40%. Plus, you have some independent variable, let's say party identification. And what we want to do here is estimate the relationship that party identification has on approval for Obama. And so X is really that, degree of partisanship. And then E epsilon is simply some error that is unexplained variation in Obama's approval that we don't know what explains it. It's whatever's left over. So then what we would do is we're going to use R's regression function, and we're just going to say, which is LM, and LM just means run a regression. And we're going to say regress Y on X and give us the output in this object called N1. We regress Y on X, and then we want to see what the estimates are, so we use summary function of the output from the regression. And what we get here is the constant or intercept estimate is 0.5 with a standard error of 0.03. The t-value is 161, meaning it's statistically significant. It's statistically different than 0, that this number is 5. We also get X, that's 9.98, with a standard error of 0.03. And so this is a little higher than the true population parameter of 5, but if you minus the standard error, right, then that becomes 5.01, which is pretty much nails the true population parameter. And if you add the standard error to the x estimate of 9.98 here, we end up with one that's 10.01. So again, we're getting an answer that's perfect, a perfect estimate or an unbiased estimate of the population parameter. Now maybe we do this once and it's a fluke. So what a Monte Carlo simulation would do is do this again and again and again and see how often we get the correct answer with OLS. What I'm going to do here is create an empty matrix called MOLS, and this is just an empty matrix with 2 columns and 1,000 rows. And what these are going to do is store the intercept in one column, and it's going to store the estimates of the beta coefficient or the population parameter estimates in the second column, and it's going to do this 1,000 times. We're going to, again, basically create x from a random normal. Beta 1, the constant is going to be 5. Beta 2, the population parameter is going to be 10. And then this is just a loop in R that says run OLS 1,000 times on different samples of data, and then save that into these columns of this matrix that we call OLS. So let's do that. And we're just simulating regressions over and over and over again. It's already done. And now our MOLS matrix is no longer empty. Now it has a whole bunch of estimates in it, and you can see these all 5, 4.9s, right? So again, looks like we're getting the right answer. These are all 10s, 9.95, 9.97, right? Again, looks like we're getting the right answer. We can get a better sense of this if we graph our estimates in a histogram. So here we have 1,000 estimates of the constant or intercept, and we can see most of these bunch up, the mass of the distribution is at 5. Most of these range between 4.9 and 5.10. So there's a few outliers here, but overall, OLS has given us the true estimate of the population parameter. If we look at the slope estimate, it's centered around 10, between 9.90 and 10.10. Again, this shows that on 1,000 different trials of different samples of data from this population, OLS is giving us the correct estimate of the population parameter. So through Monte Carlo simulations such as this, we don't have to actually mathematically derive that the statistical estimators we use are giving us the correct answer. We can actually show that on some data that we create where we know the population parameters that we're able to get the correct answer. So this should give you hopefully a little bit more confidence in what you're doing here, or what you're learning.